I'm
The
hoping.
framework for composition, a step towards a foundation for assembly and introduction.
I think actually, Wendy, we should do this as a duo. I will do the slides and you can do the voice. Let's try. Should we try it with the next slide? There we go.
Okay, next slide, Chris. I'm going to shut up now.
Okay, I think it was much better with you. I don't know. Yeah, they're going to get people are going to be pissed off. There's going to be people in the chat demanding we want Wendy back. Anyway, this paper is. I think I was asked to do this, I think a week and a half ago. It was over a week ago, my memories fade. So I think it was in the last week or two. And there's a paper we're producing called A Framework for Composition. It's going to be issued soon. I think Matthew will probably know the details, or someone will know the details of when it's issued. I'm a small cog in terms of the publishing process. It's part of the foundation data model, which is part of the information management framework, which is part of the UK National Digital Twin, of which Mark Enzer is in charge. So that gives you like I'm 4 layers below Mark, apparently. The aim of this paper was to try, well, it started off at looking at components of assemblies for schools and other sort of social structures. And what comes out of assembly is there's inherent in the notion of assembly is this notion of composition. And one of the things we're trying to do with the FDM, one of the themes that we get repeatedly beaten up for, is trying to build something that will last for decades, because if it's not something which you can change all the time. It needs to be really solid. So the question was, what would be a solid foundation for composition? And in a sense, the paper evolved from that question. And it turns out that at the center of this notion of composition, or so we claim, and I'm hoping we're going to have time for questions, because I'm hoping people are going to come up with challenges, which would be good, because then that would make the product more solid, is the notion of a component breakdown, where you have a composite whole and it's broken down into its components. And when you start looking into this, I mean, I knew quite a bit of this before, but when I started looking in more detail, it's got a really rich underlying formal structure, and that's described in the paper. And also, this other thing that we've done in the paper is we've turned the analysis of the structure into an assessment framework. We did the same thing for the TLO, and the idea is you can look at your existing models or your designs for the new models to see how well they fit in with this. And if you think from a National Digital Twin perspective, if you've got data coming in, you really want to see how solid it is, and this gives you a tool to make those kind of assessments. The goal, the paper is I can't think how many it is, 40 pages or so, and it is quite technical, and it's one of those weird things. I think there's a story about Einstein's relativity, is that once you've understood it, was really simple, but even in the 30s, there were professors of physics saying, I'm sure this is wrong, I don't understand it. So I think just being simple doesn't mean that it's easy to get your head around. So what we found as we went through is that because we're having to tighten up the formalization of some of our notions and something to get the structures right, it is quite difficult. So I think when you trawl through the paper, I'll just warn you, you might want to read it slowly. But as far as the presentation is concerned, we're trying to explain, if you like, the reasons that drove us down the route where the paper ended up. Our structure is we're going to try and give you some sort of flavor what composition is, trying to situate it so you've got some feeling about what's going on, and also that try and get a feeling for its rich history and the richness of the things going on. So quick look, not doing it justice to it at all, about how composition is modeled, just to give you some sort of feel about, if you like, what's gone before, and then reflect on the formal structure that's emerged from the quick tour, the whistle tour that we've had of the stuff. And then we'll do a little bit, we'll just go through the highlights of the proposed formal structure to give you a flavor of what's going on. And I don't expect all of you will be so amazed and enthused by it that you'll immediately demand the paper and you'll read it carefully for the next week. But I'm hoping that 1 or 2 of you might fall into that category. So what's composition? It's always interesting to look at etymology. The etymology here is taken from the English words, which as a national language doesn't really go back too far beyond medieval times. But you can see that there are links back to Latin here, and I'm sure you get the same sort of structures if you went back to ancient Greek or ancient Latin. The theme that comes out is this idea is of uniting two or more things into one, or taking one things and breaking them down into different things. So we've got here make or form. I've got to be careful like clicking because I think that doesn't highlight it or get me to the next thing, and then made up of distinct elements. If you go back to something which is I also think is useful, if you look at if you like the intellectual history, and by the way, this is Western biased. It would be interesting to look at, if you like, what would happen in Asia and Latin America and other parts, what goes on. I would be surprised if there is a different structure. That would be really interesting if there was one, and certainly if anyone knows anything, yeah, it'd be really great if you could get in touch. Again, I've truncated here. Boethius, is it late Roman or early medieval? I don't know, but the ancient Greeks had there's quite a lot in Plato and Socrates and so forth, Plato and Aristotle. But again, we've got here, let's go with Leibniz, the parts taken together differ only in name from the whole. So the idea is that if you take a number of parts, and of the right kind of parts maybe, and combine them in the right way, you get a whole. Hopefully the range of, I mean, Boethius wasn't 1988, I think it was the 6th or 7th century AD. Anyway, you can see that the same sort of pattern of thinking occurs. So it's if you like, it's something that's relatively common, that's relatively ancient, and there seems to be a commonality to the theme. An understandable commonality maybe. So let's look at some examples. This is actually for the the arm that's holding up the screen that I'm looking at the moment. It's taken straight from the manual. First of all, there are two interpretations. I think this is going to be important as we go forward. There's one that's sort of a general thing that dual stacking arms in general have, and I'm not sure, is that a nut? I'm not a mechanical engineer. The mechanical, that's probably a bolt down at the bottom there in 4A. Anyway, whatever these things are, what we've done is that they've cut down in a certain way these things into the set of parts, and this is the idea, is this is complete. I mean, they've got a multiple here, 8 times and 4 times and 2 times, but this is a really complete breakdown of what you need in order to build this. Next example, I wonder I'm just trying to remember what the next slide is. Oh, there we go. Yes. So I think one of the things is that this example is slightly misleading in the sense that when it arrived in a box with all of these parts, and then it was assembled into this. And one of the things that I didn't actually was written in the slides I didn't mention is there's a distinction between what could be called an integral component and a replaceable or temporary part. And there's quite a lot in the literature, and the idea is, maybe sort of making it more personal, is that I've got my heart, and if I have a heart transplant, the new heart is still my heart. So my heart's still there. Or in the case that we've got here, the more mundane case we've got here, if my car has a front right wheel with a tire, if I change the tire, it's still got a front right wheel. It's the same front right wheel. The thing doesn't change. And so the thing we're talking about is the car's front right wheel, not the particular tires that it has during its life history. So as you can see, I don't know whether you can see my cursor, maybe the screen's not big enough. There's this orangey thing that says integral component that talks to the tire component, which is a part of the car object, whereas these individual tires, tire number 22 and tire number 21, sometimes they're part and sometimes they're not. So that in that case, they would be temporary parts. And we're talking about the relation here between the car object and its integral components, the tire components, not about the replaceable parts. I mean, obviously, for the bigger story, you need to have a story about replaceable parts, but the thing that the paper focuses on is the integral parts. Again, just to go through the example and notice again, you've got the two things you can say. Let me get it right. The digital arteries are parts of bodies, or my digital arteries are part of my body, or my femoral artery is part of my legs, or femoral arteries are part of legs in general. We've got these two things, and there is a subtle relationship to this. It's not simple one-to-one that needs to be explained. And we're just trying to look at the way in which these breakdowns work. You can see that you've got a whole, you've got parts listed here. This is easier to see what the parts refer to. Hopefully, I think in the next few diagrams we've got some things that shows the structure more rather than, but probably is less easy to see what it's talking about. Yes, there we go. So in this next thing here, we've got the actual structure, and you can see the breakdown. So products breakdown. I was looking at this earlier into skin products, opening products, and I'm sure the people who work in construction will tell me that skin products aren't the sort of things that you put on your skin, which would be my initial reaction. And again, you get opening products breakdown. So we've got this breakdown structure, which at each level you break down completely down to the next level. Let's see what's next. And this is quite important here. This is another piece of work we're doing. We're looking at breaking down on engineering breakdowns, and you have a notion of a functional class, which is the function that the equipment is going to perform, and then you have a procurement class, which is the type of thing that's going to be procured, say from a particular manufacturer with a particular a particular specification and so forth, that meets the specification that the design engineer put on the functional class. And as you can see, what you're doing is you have this hierarchy behind, and you're making a slice through the hierarchy. And sometimes it'll overlap and sometimes it won't. So different component breakdowns can either reuse components or use different components, but they're essentially, each component breakdown is making a choice about how it cuts up reality in a way. This is interesting. This is a really good book. I can heartily recommend it. Wimsatt's Re-Engineering Philosophy for Limited Beings. But the particular point here is interesting in the sense that it starts to make you think about the way the decomposition works. So the point that we're interested in, you can read the text if you want to, but I think it's these two highlighted items here and here, is that if you've got something that's relatively simple like granite, when you do these different breakdowns, so here's an example of 4 or 5 different breakdowns, it breaks down, as you can see from his picture, it breaks down in the same way. So the components are the same. So you have, well, as he puts it, you have spatially coincident boundaries for parts. If you look at the common fruit fly breakdown, what happens is that each of the breakdowns cut in a different way. So even though these parts will all overlap, their spatial boundaries aren't coincident. So in a sense, the reason this is here is this, it's giving you this feeling for you're making a choice, or your purpose leads you to make a choice in which boundaries you end up with. And in more complex cases, you have to make more sophisticated choices. You can't reuse the choices from elsewhere, whereas in simple cases you do. So again, this is a whirlwind tour, and if you come up with if you have other examples you want us to consider, please share them. The claim, or what arose when you look at it, is that we're really, from a formal perspective, bear in mind we're trying to look at formal structures here. In the paper we talk about the material structures, the specific material things, but in the presentation we're sticking to the formal. There seem to be 2 formal structures, one which is a binary relation and one which is an n-to-1-ary. Now, this is a neologism, and so apologies in advance, and people are used to one-to-many and many-to-many. Everyone's first reaction is to say, why don't you use them? And the problem is they're describing something different. So hopefully when I go to the next slide or the slide after, it'll become clear what we're trying to describe. And it's actually a different kind of relation. And one of the things that surprised me, one of the things that I felt niggling me as I went through, was how this kind of relation doesn't fit into a lot of the normal conceptual modeling ways of doing things. I can see there's 15 things on the chat, but the way this the presentation works, which is probably a good thing, is I can't get hold of any other screen. I can only see my screen. Okay, so by the way, if it's a clarificatory question, I'd appreciate, Wendy, I don't know, maybe if you stop and ask, but otherwise I'll do them all at the end. And it's great that they're 15 questions.
I'm watching the chat, Chris, and there's a lot of chat going on. You just carry on and we'll pick it all up at the end.
So the examples of whole parts, if you're into Mereology as a branch of ontology and philosophy, it's been really well studied. I think in '87, Peter Simons published, I've probably got the date wrong, his amazing book on parts. And there's a new book coming out soon. It should have been published. I don't know why it isn't, from Cotenoir and Achille Vasi, called Mereology, which is, if you like, going to last hopefully for another couple of decades. But in that gap between '87 and now, there's been an enormous amount of research on Mereology, and enormous, well, being philosophy, there are exceptions, but the core of it is there's a simple binary relation, X is part of Y. They sometimes have, as we noted at the top with temporary part, you might have a third thing at time t for temporary parted, but certainly if you're thinking of standard integral parts, you have, it's a binary relation, X is part of Y. In the TLOs, you go back to the TLO survey, picked at random, a BFO first, B, a current part of C, binary relation. They've got a strange mereology, so they want to have, they separate out different mereologies for different domains. So this is the current mereology. 5096 has composition of individual. This is a bit of an outlier. Matthew and I talked about the term composition. It's a binary whole part relation and doesn't follow the traditional, what I would claim is the traditional sense of composition. So it's really commonplace. I think at where you look, in our data, we've looked for one of the things we're looking at in quite detail at the moment. Andy's doing work on this and OS open names. There are a lot of mereological relations, and they're all, you know, let's say a town is in county, they're all binary. So there's this whole, if you like, tendency towards this binary whole part relation. Interesting, we took this from the OPM standard 19450 has, and when you start looking, you find more and more of this. It looks at processes, and in processes, they're more worried about all of the parts somehow build up to the whole. Otherwise, in the case if you think about process specification, the process won't behave the way you want if you only specify half of it. Undoubtedly, someone will come up with a counterexample. But if we look at this example here, is what you note, and this is in a sense beginning to explain our phrase end to onery. And the reason the end comes first, as we went through some discussion on this, is that we have people with OCD on the project, is that the arrows goes in this direction, so we should start here. So you have n things here, the wing, the body, and the engine, and they go up to 1. And even in the iconography, where you can see with this little triangle here, is that it's got one thing at one end and it's got multiple things on the other end. And we've got another picture later on that sort of stresses this. And formally, it is a very, very, very different structure to a binary relation. And in fact, it's more like a state of affairs than anything else. I mean, in terms of the way, if you look in the mathematical side, the way in which relations fit together. Yes, I think there was one thing noted. Yeah, this is this, and I think on the list of terms, the etymology that they had, we included participation. There is a part, the part of participation. There's an idea that of composition is a bit like participation in the sense the parts together construct the whole. I think, yeah, okay, that's probably not worth looking at. This is from ISC, so Building Smart, ISO 16739. And they've got, and I'll just put the click in here. So in the Step Express language, they've got this ability to say that you relate one thing to a set. So that's what's happening here on the related object. So the related object is 1. So that would be the 1 of the n to onery, and this is the n, which is a set. And what's interesting here is there's no order and there's no repetition, which is the feature of a set. So and that's a feature of the, if you like, the formal structure of composition. So this reflects it quite well, and it's quite used. Though I must admit, when you look in the details there, it is a bit idiosyncratic. Something that there must be people here who are familiar with UML. In the UML component diagram, one of the things you note, let me just get up the thing, is that here that you could argue that the relation is implicit, but it's implicit in the structure. So if one box is inside another, it has a relation, much like a Venn diagram. And just the sheer constraints of writing box where you can't put a box half in, half out, ensures you get this breakdown structure. The only thing from a visual point of view is you might argue that the background here is empty. There's nothing. There's no process in it, but that's probably a bit too technical for most people. Okay, so what kinds of formal structure? What kind of formal structure is emerging, or formal structures are emerging? I think. What I'd like to do is go back to these two basic structures and just look at an example here. So a simple example, blocks A, B, and C together form a whole block ABC. If we look at it, and this is I think we found this useful way to visualize the structures. On the N-to-1 approach, you've got this hole here, which plays this. So the structure of the relational state of affairs is it has one thing here, and then it has a set of things here. If you remember the IFC example, or even the OPM example, a set of things which cover the whole and together make up the whole here. Now, it might look, I think when you draw it like this, it might look that you've got the same information here, but in fact, you can have, one way of looking at it is to take these two out, and that's a perfectly valid relation without these two and can exist on its own. And if you populate, when you start populating and you can put in Cyto, you can put the whole, visualize the whole part structure. It's just a network. There's no privileged wholes or parts. There's no way of saying, oh yes, these whole parts mean that this is a whole. I mean, you can work out what the wholes are by picking a whole and picking the parts, which we'll do later, but the whole parts don't do it. Whereas in the case of this components, it's a whole first. You have a whole, and one of the comments is wholeology, and in fact, I'm trying to remember who is it? The Ghost in the Machine? Kersler actually has a whole system of holons and wholeologies for systems and stuff like that, which some of you might be familiar with. And in a sense, what that's in a sense playing to the same tune, which is that there is in a sense a whole which has privileged parts and these kinds of parts. This one breakdown. It's a bit of an odd way of doing things. I don't know Kersler's work that well, worth checking, but you can typically have multiple breakdowns. So if you're trying to argue for a preferred breakdown, I think you've got a hard case to make. The other thing, and again, if someone come up, would be really interesting, is there doesn't seem to be something going the other way. So they've got wholeologies, but they don't seem to have partologies, where you have a part and the wholes that it appears in. There doesn't seem to be much much that we've been able to find in the literature. Again, a way of thinking about the structure that's useful. This structure on the left is based on the notion of the blocks ABC as being mereological atoms, in the sense you can't cut them up. There's nowhere else. And then if you generate the whole part structure, you get these. And if you see A as part of AB and AB as part of ABC, and from that transitive, you get A as part of ABC. So that's immediate part in the sense that it has something in between it. There's parts in between. So what you have in a typical whole part structure is you have mediate parts. And if this is dense, in this case, we've got mereological atoms, but if it's mereologically dense, so you believe that you can keep on, the world is gunky, you can keep on cutting down, there might be no immediate parts, because anytime you come to somewhere, if you can always cut again, everything's immediate part. So that's the reason for possibly here. So but in this simple case, it's heterogeneously immediate. There's some immediate parts and some mediate parts, but when you come to the component structure, it's homogeneously immediate. You're only connected to your nearest, and the next stage is connected to your nearest. And this is, in a sense, behind the way in which we would say, for example, we might say, let's see, an engine is part of a car, a piston is part of an engine, but we wouldn't want to say the piston is part of the car. And we might say, my finger is part of, or my hand is part of me. I'm part of a mob, but is my finger part of the mob? We get these cases in natural language where the transitivity breaks down, and I think this is part of, if you like, in the where you formalize and tidy up the structures, they become homogeneously immediate. Something that, again, if you look at the examples, you notice that the components typically cover the composite, which we've got here on the left-hand side with cover, a partial cover. The other possible ways in which the fusion of the selected components could relate to the whole don't seem to quite work. I mean, the far right one, the separation, it'd be really weird to have, let's say you've got blocks A, B, C, and X is blocks D, E, F, which are completely disjoint, maybe in another room, to say the blocks A, B, C compose this joint block D, E, F, or the block it just doesn't make sense from a composition point of view. The other thing is this, and we notice typically here, because there are edge cases which talk about in the paper. I don't think we'll have time to talk about it here, which is this idea of disjointness. And I think one way of thinking it is that if you cutting up a cake, it's very difficult to cut overlapping slices. Or when you come to design a factory and you're trying to assemble parts, you don't assemble overlapping parts. The parts are disjoint and you assemble them. I mean, be good if someone can come up with an example of, I mean, after you've assembled them in some way, you could argue they overlap, but when they're starting out at the beginning of the production line, they are disjoint. This table summarizes it. There are just 2 points that I'd like to drag out from the table. Is that there is a tendency to think of there are only one form of compositions, and depending on your background, you think of it as the taxonomy breakdown of classes, or you think of it as the breakdown of parts in an assembly. You're saying this particular, I don't know, car is composed of this engine, this body, and so forth. And in fact, there's example of 2 domains, but actually there are quite a few domains in which you can probably see the composition structure, and it's a formal structure. So if you can create a whole part structure, you can create, and I think we'll come to this in a second, a formal structure. So there are multiple domains in which this formal pattern reoccurs. And the other thing within the domain, the whole parts seem to typically be a single global structure. There are oddities that that you can see in certain places. There are quirks, and not everyone necessarily subscribes to that. There are outliers, but this seems to be the case. And it seems, again, it seems to be the case that in general, most people accept that within this single global structure of whole parts, you have compositions, and there are multiple ways of doing composition. So if you remember back to Wimsatt's diagram and the fruit fly, we had 5 or 6 ways of breaking it down. That seems to be the normal, or like the standard way that these things break down. The other thing, in a sense, which in some of my comments I hearken to, is that composition can be a restriction of the whole part structure. You've got the whole part structure as the background, and you can impose your compositions on top, or you can see the whole part structure. You start with these composition structures, and this may sound a bit odd, but hopefully when you get to the end, you'll see how it works. You can start with this composition structure, and you can see whole part as a relaxation of the structure. Let's see, okay. So I think, in a sense, I'm just repeating stuff that I said earlier. If you have a part structure, and the part structure is flat in the sense that it doesn't seem to have a hierarchy built in it when you look at the parts. When you try and, if you take any particular domain that you're interested in, you get all the possible parts you can. In general, there doesn't seem to be, it seems to be flat. There doesn't seem to be a hierarchy, but there is a way of finding a simple sibling hierarchical composition structure within this, in fact multiple, and you can go the other way. You can start with a composition and you can extract a flat part structure from it. What I'd like to do now, if I can, this was done in a hurry, so I'm not sure, let's hope, is yes. So I'm going to try and, if you like, take you through the first thing. So start with a flat part structure and show how you can get the composition structure to try to get you to the feel for how this works. And this is a simple example, and I'm sure there are many, if you like, the graphics I'm using can be improved in many ways to show what's going on. So the first thing is, yes, we've got a transitive reduction. So we're only showing for the things that are in scope, the immediate parts. So for example, on this thing, I don't know if you can see my cursor, but if you can, we've got these 2 things that are linked by 2 arrows. There's another arrow that would go, whether any 2 joined arrows, there's a 3rd arrow, or whether any 3 arrows, there's a 3rd arrow that would join it. We've left that out. So we've done a transitive reduction so we can see what's going on, and that's a common visualization trick. We're granular, and hopefully this next thing will show. So if I was to look down there, I would drill down there a whole lot more parts with a whole lot more parts relation, and I cannot carry on drilling down until I get to the bottom. And there's some theories that say there's no bottom, so I could carry on drilling forever. And also, I hope if we go back to this structure here, you can see that as it stands, there's no way of picking out particular holes and the components. or well, okay, I could choose this node here. I hope you can see my cursor as a whole, but what are the components? And that's really the thing that we're trying to illustrate in the next section. So let's say, am I going the right way? So we start with this structure that we described on the previous slide. The first thing I think you do is you need to get levels. And let's say that where the levels are water molecules and water atoms that we're just looking at. I mean, we can pick whatever we like. And when we've done that, we then need to do the breakdown. So this will be a water molecule, and these will be the two hydrogen atoms and the oxygen atom. And as every time I've shown this to anyone, they've said, but the hydrogen atoms are bigger than the oxygen atoms. I didn't have time to change it. Maybe next time I'll change it. And then you basically pick the other. The issue here is the picture isn't quite right, because in order to get disjointness, you haven't picked them all. So maybe this line should have been a bit wavy. If we'd had time, we'd have done a wavy line just to pick out the atoms, and then you get the breakdown that you want. But hopefully it's enough to give you a flavor of if you were in whole part land and you wanted to move over to the composition you're interested in, the maneuvers that you might decide to make. So, okay, this is the proposed formal structure. This is, if you like, we're now trying to find a formal structure that explains all of the previous stuff that we've shown you. And it's built on a simple composing operation. We've used a funnel, which is not it's ideal from a graphical point of view, but maybe not ideal in the sense of a metaphor for what's going on. I mean, I suppose you could, if it was a mixture, you could think of it, but I think if you've got building blocks where you're bolting things together, you wouldn't use a funnel for them. Anyway, so the idea is you take your components into the composing operation, you apply the composing operation, and you get the component. You could do a decomposing operation. The issue is then you need to select which bits you decompose into, so it's more tricky. So going this way, going from the components to the composite is better. This gives you some idea of what's going on. This, if I can explain it for a second, is that we've used this irregular hexagon to represent the reified operation, and it's meant to include. Typically, a relation includes its relator. So we've got, if you look at this composing relation view, you say, the relation links these things. So you can see the things that are related, but typically often most of the standard theories of relation will have the relation inside. So in a sense, the relation is a little bit more like this in terms of its structure. And we interchangeably go between the views. So it can be a little bit confusing when you go through, but if you just remember, there is this reified atomic composition, and you can see how you can break down the composition into part relations here, and these are independent part relations. And the idea is that what you do is that, from a fusion point of view, is the composite is the fusion of the composite. So the composite is the components are disjoint, and if you add them together, they completely cover the whole. So the whole just is the sum of the components. If you want it in the language of whole part relations, we say AB is the fusion of A and B. So if you imagine then what you do, if people who might be familiar with the TLO survey, or one of the ways of doing it, the way in which our preferred way of doing it is that given a particular domain, what we do is we construct all of the possible atomic compositions. And the next thing that we notice is that when we do this, is that some bits of the atomic compositions overlap. So this BC, which is a component of this, the ABC atomic composition, is also the composite of the BC. And so if you now squint so that you forget the elements that are inside and you just look at the atomic compositions, you've got a relation between the atomic compositions. And this right-hand side with the opaque is intended to give you some sort of visualized help to try and do this. And then if I remember what the next slide is, yeah, okay. So what you're actually doing here is that if you map the full top relations across your whole domain, your whole domain is you're actually reflecting the compositional history. So if we look at these top relations here and we go back, we put the elements in, we see that they're in fact reflecting the funnels of composition. So we've got this composition relation, which is the basis for our formal structure. If we look at the histories, we get this atop relation. What's the next slide? Yeah, okay. And then we have, when we do this, we have a graph of the atop relations, and this gives us the base atop structure in the domain. Now, what we then need to do is we need to create the molecular compositions, the hierarchies that you saw earlier, like uniclass, and we do it step by step. And here are the steps where you join things in. There is this joining operation. I won't bother with you with the detail, but in a sense, what you're doing is you're choosing a particular history. And as you'd expect, if you have got a molecular composition, it has got a certain kind of history that goes with it. And the other way that you can look at it, if we go back to our top diagram, is you select a history from here. And you notice that one of the things that's interesting, if you notice that you haven't gone back as far as you possibly can here. So if you go back here, if you go back to this stage in the slide here, you will see this A, B, C, D, E, F. This particular thing, where are we? Here, this atomic composition, this ending here, by the time you get here. So this molecular composition, which is the irregular hexagon on the outside, has as one of its components EF. So which has a history, which we can see down here. So when you're choosing the history, you choose a segment of the history. You tie it with your whole, and you can go back as far as you want. So that, in a sense, that's how far you want to break down in terms of the composition history.